Okay, here's not the greatest assigned win. 1, 3 out of the first 4 of the multiple choice, the most missed. Right? Those are the questions that you'll see on tests. This was the most. Math department has 5 teachers. The ages of the teachers are 23, 34, 37, 42, and 58. You select a random sample of 4 teachers and calculate the sample mean. Which of the following shows the sampling distribution? Holy cow. 1. Oh, the sample minimum. Oh. So 23 plus 34. Oh, plus the ages and use a random sample of 4. Oh. So 23 plus 34 plus 37 plus 42 divided by 4. Should be?
No. It's just so the 4 different combinations, you take the minimum number, like value from each of those. So it'd be 23, 23, 23, 23, 34.
Why are you choosing 23 that many times?
Because that's so in your all the possible samples that you could take of 4 teachers from the 5 teachers, 23 is the minimum 4 times.
I could see how you messed up on that one. Because once you choose a 23, you can't choose the 23 again. But I could see how you could miss that one easily.
Bad question.
Yep,
So
concur.
Not going on the test.
I mean, I wouldn't see that one again.
I appreciate it.
Good. Okay. Oh, shucks. I didn't hit start. I did too. Okay. Next sample. Next multiple choice question. A statistic is an unbiased estimator if the parameter when it's unbiased. When in, I can see how you can miss this one too. This one you need to somewhat at least understand why you missed it, I hope. In many samples, in a single sample, in many samples, the statistic is calculated, and in many samples. We definitely want many samples, okay? Not only that, because that's 3 of the 5 choices. In many samples, the values of the statistic are centered. In many samples, the values of the statistic are very, very close. In many samples, the distribution has the shape that's approximately normal and you don't care. So I would guess, I'm hoping that the answer is in many samples, the value of the statistic are centered at that value. It should be A. Not close, it should be the same. Okay? And then one more. Oh, it's over here. Centered, yep. Increasing the sample size of an option poll will reduce the variability of the estimates made from the collected data, the bias, the effect of the variability of the opinions, and the variability of the opinions in the population. It's definitely the sample. It's definitely the sample. Okay? All right. You don't think that was the answer? The variability of the estimates made from the data collected?
Yeah.
Well, because you're estimating. Huh? There you go. Hopefully you learned from the ones you missed, because I just did. Here we go. 7-2. AP Stats. Drive. Pop, pop. Pop, pop. Yeah.
No, going to Epic Universe.
I am. All right. Like Wednesday, if you understand this one really well, it's going to make Friday really, really easy. So almost what we're doing today is the exact same thing we're going to do Friday. Pretty much the difference is you got to recognize the differences, but there's not much. So here we go. Today, guys, we're going to talk about sample proportions. And we're talking about the sampling distributions of sample proportions. Apparently, I'll wait and listen for everybody else to get ready. We're good? Okay, sample proportions. On Friday, it's sample means. So one of the biggest things from here until the end of the year, guys, and into the school year, is to make sure you know, are we talking about categorical or numerical data? Are we talking about categorical and numerical data? If we're talking about categorical data, we're talking about proportions. So all of the questions today should be categorical data. And then on Friday will be numerical. So just kind of recognize that. When we're talking about proportions, we're talking about categorical data. What percent are white cars? You're either white car or you're not a white car. Okay? What percent of the students are seniors? You're either a senior or it's a group. It's categorical data. Okay? So just kind of recognize that as we're going through today's lesson. Okay? Clicky, click, click. Why are you not clicky, click, click? Clicky, click, click. Okay, first we're going to talk about the sampling distribution of p hat. Okay, now you know the definition of the sampling distribution. All possible samples of the same size from the same population. All possible samples of the same size from the same population. Well, the sampling distribution of p hat is very, very similar, except we're going to just put a little bit more instruction on that. Is the distribution of all possible p hats of the same size from the same population. All possible samples of p hats, all possible of all the p hats of the same size from the same population. On Friday, it's going to be all possible samples of X bars of the same size from the same population. Again, that's Friday. So we kind of understand what a sampling distribution is. It's every possible sample of that size from that population. Whoop, dadgummit. How do I get rid of that? Exit. Go away. Yay. Apply. Slideshow. Sorry. Sidebar. Okay, so we know that the sampling distribution is all samples of the same size from the same population. Now we're going to get all possible p hats. We'll kind of go through this today as we go, and hopefully it makes a little bit more sense other than just words. Okay? By the end of the section, you will be able to anticipate. You will be able to anticipate three things: the shape, the center, and the variability or the spread. You will know exactly what the shape of the sampling distribution will look like. You will know what the center of the sampling distribution will look like. And you will know what the spread or the variability or the standard deviation of the sampling distribution will look like. And if you know those three things, we can find the probability of a lot of them, because guess what the shape's probably going to end up being? Normal. Okay? So if you can predict those three things, and we can find a lot of probabilities by using our normal CDF or by using Desmos. So, all right, here we go. Soak this in for just a little bit. Orange Reese's Pieces. So Reese's Pieces are the delicious candy. Not really. I don't really like them, but whatever. What are they supposed to have? Supposed to have peanut butter inside of them? We're going to take a sample of those Reese's Pieces. So I'm going to reach my hand in those and grab some out. Some of them will be orange. They will either be orange or they will not be orange. If they're mixed, then I'm throwing them away. Click. Not that you care, but you might. 7 things to know about Reese's Pieces before we eat them. There's the picture. Get up there. As much love as Reese's peanut butter cups are, let's be real. They're not exactly conducive to popping by the handful without serious judgment. So that's why the beauty of Reese's Pieces comes in. They give you the same creamy peanut buttery flavor. Actually, they don't even say close to an actual Reese's cup, I don't think. Anyway, you like them? Okay. They give you the same creamy peanut butter flavor, yada, da, 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 da. They aren't made with the same peanut butter as actual Reese's. They're not. Food, though they taste similar, Hershey's actually developed the formula back in the 70s for the sweetened peanut meal that has consistency of chocolate, which becomes the basis for the Pieces, said a spokesperson for Hershey's Cameron. They weren't Hershey's first sugar-coated product. That was the first, which we know now to be M&M's. Hershey's developed the ability, they weren't the original name. It was Hershey-ettes, which were candy-coated discs. They were eventually discontinued. Again, this you don't care. E.T. saved Reese's Pieces. Movie E.T., anybody seen? It's a really, really old movie. After a successful launch, Reese's Pieces sales started declining. Luckily, around the time, Hershey's got a call from Universal Studios saying that Steven Spielberg wanted to use the candy in his film. They agreed. Hershey's would help support the movie by way of trade promotions, consumer products, and displaying features E.T. And in return, Hershey's would have exclusive confectionery field, whatever, for the promotion and advertising after the film. Product sales increased by 300%. They were one of the first ones actually to get in on the movies. Pepsi's done it now a couple times with Back to the Future. Some other products have done it anyway. There's a reason you get so much orange. This is kind of the most important part. If you're wondering why your box or bag is overloaded with orange pieces, it's because that's the goal. The candy is 50% orange, 25% brown, and 25% yellow. So that's their claim. That's what they're telling you. Half of them are orange. They're seriously very popular at Halloween because of the colors. They've ventured beyond pieces. They've done Big Cup, and they've done all kinds of other things. Who really cares? I just like talking about it, just to get your mind off this stupid crap for just a little bit. Click. Now we're back on it. Suppose a large bag of Reese's Pieces has 1,000 pieces in it. The manufacturer says 50% of them are orange. I'm going to select a random sample of 50. How many should be orange? 25. Would I be surprised if I got 25? No. In fact, I'd probably be more surprised if I got exactly 25, maybe 26, maybe 24. Would I be surprised if I got 0? Yes. Would I be surprised if all 25, or sorry, all 50? Yes. Watch. Let me play my game. Reese's Pieces. Probability of orange, 0.5. Number of candies. How many did we draw? 50? $50. Here they come. 24 of them. Close. Proportion. I'm going to do proportions, not numbers. Okay? So it's 49%, right at it. Beautiful. That's one sample. That's not anywhere close to the sampling distribution, right? Very long. Let me play. It's fun. Ooh, holy cow, 32%, quite a bit lower. Y'all okay with me not showing the animation? 66%, holy cow. 50% dead on. 54%. Somebody's late. There, I just did 10 of them. The last one I did was 42%. Y'all okay? Boom, I just did 10 more of them. There's 52%. I want to do 100 of these. Actually, let's do 500 of these. A lot of times our books will do 500 of these. We're simulating it. Oh, now looky kind of what my picture looks like. Good. And if I did 500 more of those, I even have a better picture. And if I did 500 more of those, I probably still don't have a sampling distribution, but I got a pretty good distribution of samples. shape is normal or approximately normal for sure. The center is right about 50. Amazing how that happens. You're kind of okay with all that stuff? It's stuff that you expect to find. 72% we don't expect to find. 64 is starting to become iffy. This has got 40%, actually 38% starting to become iffy. Everything less than that we don't expect to find. You've kind of seen all this stuff several times. Again, this is kind of the big picture statistics. Here we go. Click. Now I need this button. Click. What did each dot represent? A sample of 50 Reese's Pieces, or the percentage of orange out of a sample of 50 Reese's Pieces. Y'all okay with that? We've done that several times. You need to recognize what each one of those dots represented, okay? Let's see what happens when P is small and we take samples. So now let's kind of do this for just a second, okay? Bear with me. Let me go back to, where'd it go? Here it is. Clear, clear, reset. I'm going to change the probability of orange to like 0.1, okay? And I'm only going to draw 10. Oops. Show animation. Boom. Good. Beautiful. Good. Now we get the idea. Let's don't do any more animation and let's do 1,000 of these. Uh-oh. I did 10,000. That's good. Woo. Skewed to the right. P was 0.1. P was 0.1, and I took a sample of size 10. P was 0.1, and I took a sample of size 10. That means 0.1 is probably going to be the highest one, which it is. Amazing how that happened. I'm going to change this to 0.9. You guys being brilliant mathematical students, if 0.1 is skewed to the right, 0.9 is probably skewed to the left. Reset. Poof. Sure enough, 0.9 skewed to the left. What's the center? 0.9. Amazing how that happens. Now here's where I want you to see something really interesting, okay? Because we did 0.5 earlier, right? We did 0.5. Let me reset that again, draw those. We did 0.5 earlier. 0.5 was normal, 0.1 was skewed to the left, and 0.9 was skewed to the right. Now watch what happens. I'm going to change this back to 0.1. I'm going to change this to 0.1, but instead of drawing 10 candies, I'm going to draw 100 candies. Okay with that? It was skewed to the left. Oh, I'm sorry, 0.1, skewed to the right. But now it's normal, approximately normal. But the center is still at 0.9. That center is still at 0.9. I don't have hardly any of those really, really, really small ones. Change this to 0.9. Remember, it was skewed to the right. Clear that. Draw them. And now that one looks what? Approximately normal. This is a very, very important thing we need to understand about statistics. Very, very important thing. And it's one thing we mentioned last chapter that we're really going to emphasize now until the end of the year. It was skewed to the right. The mean was 0.1, the standard deviation, who really cares? Let's see what happens when it's 0.9. Now they use 25, I use 10. That's skewed to the left with the center at 0.9, right? 0.5 was normal or approximately normal. 0.9 skewed to the right, 0.1 skewed to the left until I got to a lot of candies. And when I got a lot of candies, they all looked somewhat normal. So that's the big part, okay? We've already seen what happens when P is 0.5. When it was 0.5, it was approximately normal. It looked like that. Shape of the sampling distribution. Remember that there's three things we got to get out today. The shape, the center, and the spread, or shape, center, and the variability. The shape, it will be approximately normal as long as that large counts condition is met. As long as that large counts condition is met. We talked really small about that during the binomial distributions. That large counts condition, guys, if you guys can remember, n times p better be bigger than 10. And I'm going to change that just a little bit. I'm going to put p hat because that's my sample size. That's my sample proportion. Maybe I may not change it. I don't know. Yeah. But also what? Both of those have to be bigger than 10. If both of those are bigger than 10, then my shape will always be approximately normal. I had 0.9 earlier, it was skewed to the right, but 0.9 times 10 is not bigger than 10. 0.9 times 100 is. 0.1 times 100 is. When n times p and n times 1 minus p are both bigger than 10, then my shape will be approximately normal. And that's huge. That's huge. So not only do you have to know that, you have to prove this. You have to prove this. Because if you don't prove it, then we don't know it. And that's a big thing for AP Stats, is make sure that you prove that this is true. And if this is true, you know the shape. If you don't prove this is true, we don't really know the shape, even though you do. Y'all okay with that condition? Next one. Oh, that's that part. They used P. Sometimes we'll use P, sometimes we'll use P hat. If they tell you what P is, what is P? It's the population proportion. If they tell you what it is, use it. If they tell you what it is, use it. If you don't know what P is, then you have to use P hat. Again, I mentioned on Monday, it's very important that you distinguish between the populations and the samples. And if you know what P is, use it. But if you don't know what P is, then we have to use P hat. That will come up in our examples, okay? Now, the mean or the center, right? Both of these mean the same thing. Well, what have we noticed about all those centers? The center of 0.5 was at 0.5. The center of 0.9 was at 0.9. The center of 0.1 was at 0.1, and it didn't matter what the sample size was. So that's what they're going to say. Read what it says. That's the center of every single P hat. All the P hats, which is the sampling distribution, will be equal to the population center. It will be equal to it. No doubt about it. There's been a lot of people to be able to do these, and that's what it has to be. The center of all the P hats have to be equal to the population average. They have to be. So now we know the center, now we know the shape, now we need to talk about the spread or the variability. And what we talked about on Monday, we said what? As my sample size increases, the variability decreases down. And so we have to have some kind of formula that's going to associate the spread with that sample size. And so here, and we're going to call it the standard deviation. If you want to call it variability, you can. Right? All three of those things, or standard deviation, variability, spread, they all mean the same thing. Okay? This is what we use to find it. These are the words we use a lot. Okay? And it's going to be equal to, so again, notice the notation, the standard deviation of all the P hats. That's why they write it like that. The standard deviation of all the P hats will be equal to the square root. Why the square root? Because we always take the square root of variances. We have a P, and the 1 minus the P, and we're going to just divide that by n. These formulas are on your formula sheet. They are on your formula sheet. This one and this one are on your formula sheet. However, I really believe you won't need them because as many times as we use them, you guys will get comfortable with it. If you brain fart, they're on there. So now, guys, you know the center, you know the spread, and you know the shape. Hit me. Yes. I think actually after last year they didn't give you a paper formula sheet. I think this year they'll give you a paper one because a lot of the students were complaining that you pull up the formula sheet and it hit everything and it messed things up. AP Stats was one of the first tests. After that, I think physics they gave them on paper. Anyway, yes, you get one on the blue book and or paper, both. Everybody okay? Shape, center, spread. I'm done with this lesson for the most part. Here we go. Oh, gosh, I always forget this. They added this a couple years ago. Now, this is where students mess up sometimes because they say n times p and n times 1 minus p have to be bigger than 10. This is the 10% rule. That's different. It's completely different. Has nothing to do with that. Okay? So kind of make sure you separate those two things. N times p and n times 1 minus p have to be bigger than 10 to prove normality. This one, I want my sample size to be less than 10% of the population size. Completely different than the 10 or the normality rule. My sample size needs to be less than 10% of the population. Or if you want to be mathematically correct, 10 times the population. I guess that's the other way around. I don't want to mess that up. I think I messed you up. Click. Sample must be less than 10% of the population. The population could be 10 times the sample. If the population is 10 times the sample, then the sample is 10% of the population. So either way, that's what I was trying to say. Soak those three things in your head, because if you know those three things, guys, this lesson's, we're done. We're done with it. Let's prove it. In order to use the mean and standard deviation formula, the 10% must be checked. In order to use that 10%, or in order to use this standard deviation formula, that 10% must be checked. So that's where students lose points. Not by checking the 10% and not by checking the normality. They just assume it's going to fit. So they just go to town with it without verifying it. Okay? Verify it. Verify it. Large counts must be checked and verified. If we assume that the sampling distribution is approximately normal when it ain't, it's wrong. We're flawed because we can't find the probability if we don't know it's normally distributed. All right, here we go, guys. Here we go. Jump into the examples. Suppose that 84% of students at a large high school regularly use a backpack to carry their books from class to class. I stop right then and I do this. I do that. The more stuff you write, the last test, guys, and hopefully I really want to get to that at some point, but where you guys got dinged is by not showing enough work. Most everybody got the answers correctly on, especially the normality ones. You guys did a great job finding an answer. Just some of you guys got dinged because you didn't put the right stuff. You need a picture, you need a mean, and you need a standard deviation. Imagine an SRS of 100. Calculating p hat. I don't know if I had to write that down, but I do. Now, that's where they stopped right now. I don't know what this means, but that's what all they gave me. Everybody okay? Good? Any question about that? Notation is important. Why did I use a P? Because it was all high school students. It wasn't the sample. That was all high school students. Identify the mean of the sampling distribution. Again, notation is very important. I could cheat right here and probably say 0.84 and you'd be okay. I would probably even go this far. That would be like a perfect answer. Mu of p hat equals 0.84. P hat equals at 0.84 would get you dinged because we don't know what that's p hat. Don't say p hat is equal to 0.84 because we don't know. You can say p equals 0.4 or 0.84. And they'll be okay if you did that. But they really like that. That's one of those that if you ended up at those half points, if you did this part, they'd probably bump you up. Okay, next question. Oh, there it is. Calculate and interpret the standard deviation. And then they say verify the 10% rule. They're not going to tell you that on the test. N equals 100. I don't know that that's less than 10%, but it does say it's a really large high school. So I'm going to go ahead and say is less than 10% of all students. How do you know that? I don't. I'm just putting it down because they told me to. I don't know that it's not true. A lot of times this one's assumed to be true. And again, that's why students forget to put it, is because it's so obvious, but you have to put it. And now I'm going to calculate the standard deviation. So I'm going to go over here and I'm going to say that standard deviation of p hat, again, that's very, very proper notation, square root, and you're okay with putting 0.84, 0.16, 100. Just plug and chug right into the formula. And you may have to look at it for a couple times, but after a while, you're going to remember N times Q divided by, P times Q divided by N. And now you got to go to Mr. Calculator and do some little punchy and hit enter, or you don't even have to. If you leave it like that, they'll give you credit. Click. 0.0367. Ooh, I always forget. And interpret. And interpret. In an SRS of 100. Now that's important. The sample proportion typically varies. So again, now we got to start, we've talked about this interpretation of standard deviation a lot. Now it starts to get confusing, is because we got a lot of different standard deviations or a lot of different interpretations for it, the same thing. We're talking about a size of 100. So we have to, because we use the 100, I can do it right here. Because we use the 100 in it, we got to talk about the size of 100. Because if it was a size of 400, it's going to deviate more or typically vary differently. If it was a sample size of 20, it's going to deviate differently. So we have to talk about the size of 100. Typically varies about the mean. And that, I mean, that doesn't change. We've always talked about it typically varying about the mean, or from the, they said the true proportion. You're okay saying the true proportion. You're okay saying the word mean, even though means is typically numerical data. Everybody okay? Just got to make sure we got to add that 100 part. Beautiful. Nothing too hard yet, I hope. Pencils, 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 we're safe. Click. What if we thought the standard deviation, oh, this is not in your notes. I always forget to cover this, so I put this in here now. What if we thought that standard deviation was too big? In other words, 0.03 is too big. Actually, that's not really big. 0.03 is pretty small. But I thought it was too big. I wanted one that's half that big. I want one that's half that big. Well, you guys know if I want a smaller standard deviation, what do I have to do? Increase my sample size, right? Well, if I wanted exactly half, this is where we got to use just a little bit of common sense mathematically. If I wanted exactly half, a lot of students just say, well, I just need to double that. No, you can't double it, because what are you doing to that sample size? You're taking the square root of it. So you can't double it. If you want it half of it, then you have to quadruple it, because the square root of 4 is 2. And so whatever this number is, if you want half of it, then you want half of this. And if you want half of this, and you put this inside of here, the 1 goes inside there, but that 2 now becomes a 4. If I wanted a third of it, I would have to multiply it by 9. If I wanted a fourth of it, I would have to multiply it by 16. So you'll see a couple of questions like that throughout the year. Hey, that standard deviation is too large. I want to shrink it down some. What do I need to do? Increase the sample size. How much? Well, it depends on how much I want it smaller. If I want half of it, I got to quadruple it because it's the square root of that number. Y'all okay with that? There'll be a couple questions on your homework on that, and I always forget. I forgot to put it on your notes. So how many more people do we need? Okay, now they want me to describe the shape of the distribution. Well, my bet is it's approximately normal. And you got to use the word approx. You can't abbreviate it, approx. But you can't say it without proving it. So let's prove it. N is 100 times P, which is 0.84, which is 84. And 100 times 0.16 is 16. Both are greater than 10. Any questions about how I showed that or anything else? N times P, N times 1 minus P. Go ahead and tell me that's 84. Go ahead and tell me that's 16. And just say they're both greater than 10. And if they're not, I can't say it's approximately normal. Because 100 times 0.84 is 84, which is greater than or equal to 10. And 100 times 1 minus 0.84 is 16, which is greater than or equal to 10. The sampling distribution of P hat is approximately normal. Do I expect you to write it just like that? No. If you write it like that, you're going to be really, really, really good, though. Because that's what we're talking about. We're talking about the sampling distribution of P hat. Questions? Again, it's a little bitty things. It's not, the overall picture is not that bad. It's the little bitty things, interpretations, not proving something that kind of get us. But this really is an easy lesson, provided you remember how to do normal CDF. Okay, here we go. A polling organization asks an SRS of 1,500 people. I stop right then and I say 1,500. I'm writing stuff down that they're going to give me. How far away their home is. 35% of all first year P, all first year college students attend college within 50 miles of their home. Find the probability that a random sample of 1,500 will give a result within 2 percentage points. Ooh. Find the probability that it will give it within 2 percentage points. Why did I put a P hat right here? Because I'm asking about the sample. And I want it within 2 of these. So if I want it within 2 of these, then that's 37 and 33. And now I got to do some things. First thing I'm going to do is show me the shape. N times P. N, 1,500 times 0.35. Well, that's a really big number. 1,500 times 0.65. Go ahead and tell me what those are. Okay, tell me what those are. 525 and 975. Okay, so approximately normally distributed. Psst. I don't even put it in words. I'm going to have a picture this time. The center is at 0.35. Notice again my notation. Mu sub P hat is equal to 0.35. 0.35. And the standard deviation of p hat is equal to, and somewhere over here I've got to do this. Standard deviation of p hat equals the square root of 0.35, 0.65, 1, 15, 0, 0, 0.0123. Uh-oh. Dadgummit. Too fast. Point 0.123. Sorry, guys, I'm to y'all's back. Bad. Up. 1,500 is less than 10% of all first-year college students. First-year college students. If you don't put that, you're going to get dinged because you can't prove this works unless this is true. Well, it's true. Well, you better prove that it is. And so then go over here and put 0, 1, 2, 3. And then I'm going to go 33. And I'm going to go 37. And I'm going to shade that in. Again, guys, I'm telling you, most of you guys do really, really well at finding the answer. It's the points or the stuff that gets to it that sometimes are getting some of you guys. And so now I'm going to my calculator, or I'm going to Desmos, or whatever you guys decide you want to do, right, to find this answer. And you don't have to say you're doing this. We know that you're doing this. Normal CDF. Normal CDF from 0.33 to 0.37, with this being 0.35 and this being 0.0123. You can do the math right here. You can write the square root of P1 minus P all over N. It'll do the, oh, I forgot to do that part. It'll do it all for you right here if you want to. Paste it. Answer 90%, 89.6%, whatever you want to put. Apply. Make it big. Enter. What was it? 89. 0.896. Yes, no, maybe? What question about any of that do you have? Because you're going to do this about 20 times. Y'all good with a normal CDF, right? Or no, some of you guys using Desmos, and that's fine. Use Desmos. I don't care. Desmos is a little bit better because it kind of gives you the picture and it kind of gives you the probability statement, right? Desmos helps you a little bit in kind of making sure you put down everything you need to put down to get your points. How this point is graded right here. Well, this is graded, proving normality. You got to have a picture with a mean and the standard deviation, but you got to prove the standard deviation. I can kind of start seeing this. This ends up being quite a big, I mean, that's the answer. You know, your old math class, you got full points if you got that. In this math class, if you got that right there and you don't have anything else, you're not getting anything. You're not getting any points. They don't really care about that. They care about all this other stuff. You can miss this and still at least get 3 out of the 4. Sometimes you can still get 4 out of 4. Sometimes. Yippee, yippee, yo. What up, Z? Here's the perfect answer. Probably looks very similar to mine, except they just did a Z-score down here. I don't do Z-scores. Some of you may do Z-scores, but I doubt it. So it's from negative 1.63 to positive 1.63. Here's where Z, they put Z here because they put the negative 1.63 and the positive 1.63. I think that's important because you know how multiple choice sometimes switches things up, and they may not put P hat and they may not put 0.35 or 0.75 here. And so that kind of messes us up a little bit because it may not be the way we work it. The instructors are starting to get a lot more smarter, knowing that most of this stuff can be done with a calculator a whole lot easier. And so they're trying to make sure you know what you're doing, not necessarily how to do it. Question, question, question? Let's look at the difference between two proportions and sum that up for us really quickly, and then we'll call it a day. It's known that on any given day, 70% of the students in 7th hour complete their assignments on time. It's also known that 50% of students in 8th hour complete their assignments on time. So 7th hour is a little bit better than 8th hour. 7th hour, 70% on time, therefore P sub 1. So notice how they're doing this, guys. Rather than saying P equals 0.7, they're saying P sub point, and I might even say P sub 0.7 or P sub 7. So now I'm talking about the 7th hour. And P sub 8 is the 8th hour, and that's 0.5. So again, notation is so important for AP Stats. It's the little bitty things that seem so common sense to us because you guys are freaking brilliant that we don't want to put the small little stuff, and that's the stuff that's going to help us get our points. The counselor at school 1 selects an SRS of 100 students. So now I would say N equals 100 from, I would say N sub 1, actually N sub 7, right? They're using 1s and 2s. And 200 students from 8th hour. Why they did that, I have no idea, other than I'm trying to make sure we see the difference between them. 8th hour. Y'all okay with, again, anytime they tell me something, I'm going to put it down. I'm going to put it down. What if I don't need to? It ain't wrong. Here, let's talk about the sampling distribution of P hat sub 1. This you already know. It's approximately normal because 100 times 0.7 is 70 and 100 times 0.3 is 30. So they're both or that one's approximately normal. Over here, it was 200 times 0.5. I think it was 0.5, right? Yeah, 200 times 0.5. Both of that's 100, which is bigger than 10. So that one over there is approximately normal. So they're both approximately normal. What do we know about the center of this one? Mu of P hat is equal to 0.7. What do we know about the center of this one? Mu of P hat sub 8 is equal to, I forgot, 0.5. Right? Standard deviation. I don't typically put the formula in there. I just go ahead and put 0.7, 0.3, 100, and then I find out to be 0.0458, but please don't, the 10% is what's forgotten a lot. 100 less than 10% of all, again, notice I'm saying all, right? 7th hour students. I'm pretty much going to stop grading after I see 10% of all. Y'all okay? Good? So this part we already know. It's going to stay up there, I think. Boom. And then we talk about the sampling distribution of P hat sub 2. So write what you need to. I don't want to go so fast to where I'm losing some of you cats, because I'm telling you, this should not be that difficult. It shouldn't be. I hope it's not. It typically is not. Students do pretty good on it. Where they miss their points is the little bitty things. They know how to do everything. They just forget a couple of things. I don't want you to forget them. I don't do this part of it. I just do this part and this part. Is it wrong? No. Can you get by without it? Eh. I mean, it's not graded real hard. If you forget it all, they're not going to give you that credit. They'll be upset with that. Again, notice that they put all 1s and 2s. I would put 7s and 8s. Whites and blues. Whatever. They don't care what you do that with. They would want mu sub P hat, and they would want standard deviation or sigma sub P hat. They would want that. All, right? We mentioned that on Monday. Whenever we're talking about the population, I like to use the word all. Okay, everybody good? Now, we're getting ready to combine these two. This part where you're kind of using what we did in chapter 6. Because I know what the sampling distribution of one is, and I know what the sampling distribution of the other one is. I don't care about what each one of them are. I care about the difference between them. I care about the difference between them. Well, you guys know this. You guys are getting ready to tell me if this one's approximately normal and this one's approximately normal, and I subtract those two, that shape has to be approximately normal. As long as the sampling distribution of p hat sub 1 and p hat sub 2 are approximately normal, then the sampling distribution of p hat 1 minus p hat 2 will be approximately normal. It will be, always, always. As long as p hat sub 1, or as long as the first one's approximately normal, and as long as the second one's approximately normal, the difference will be approximately normal. Click. You do have to prove both. Prove both. You don't combine it. You prove this one, you prove this one, and then that has to happen. The mean is equal to the subtraction of the two means. 0.7 minus 0.5 is 0.2, just like we did last chapter when we were combining variables. If you wanted the difference, you subtract the two means. If you wanted the sum, you add the two means. Boom. And then what about the standard deviation? You don't add standard deviations. We have to add the variances. And so that formula looks horrendous. It looks horrendous, but it's not. It's a big old square root, because you had to square each one of those individual square roots. So if you square the square roots, then this square root went away, and this is p 1 minus p over n. And you square that one, and it went away, so that's p 1 minus p over n. And we always, 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 always add. Always add. You never subtract variances. You never subtract standard deviations. You always, always add variances. And then we had to put the radical over the entire thing. And so this is when it starts looking like it's really, really bad math, but it's not. I mean, you got a lot of stuff up there that looks pretty messy. P hat sub 1, or p sub 1, 1 minus p sub 1, n1, p2, 1 minus, I mean, it looks pretty bad, but it's not. And then there's this notation right here. Sigma sub p hat 1 minus p hat 2. Again, notation. Very, very, very important. One more example. Anybody got a question? Okay. Nothing really new. It's just kind of the stuff we're putting together. The sampling distributions are new. This right here is new. And then proving normality is new. A lot of times they told us it was normal. A lot of times they told us it was normal. Now we're just having to prove that it is. Click. Oh, we got to do the 10%. Sorry. Make sure you check both 10%. Because if you don't check both 10%, this doesn't work or this doesn't work. They both have to work. They both have to be 10%. Almost got you, Olivia. Dang it. Huh? Click. Oh, just to show you guys. Click. Oh, I got to have an arrow. Right, this is your formula sheet that you guys got many, many times. Let me zoom in. Oh, not that big. Whoo. Okay. You got to go to the second page. Second page. Second page. Sampling distributions proportions. Sampling distributions proportions. Mu sub p hat, p. Standard deviation sub p hat, p1 minus p over n. They do put one more over here, and they'll put p hat 1 minus p hat over n. That's where I kind of told you, if you know what p is, use it. And if you don't know what p is, you have to use p hat. And then they put for 2. 1 minus those 2. There's that big formula there. And then there's that formula over there. That's for really later on. Okay? And then down below that, now they're going to do means. And that's Friday. Click, click, click. Your teacher. I hate this ad. I hate this. I hate this example. It ain't going to be this teacher. Bring 2 bags of colored those to class. Bag 1 has 25% red. Bag 2 has 35% red. Each bag contains more than 1,000 crackers. Using a paper cup, you take an SRS of 50 from bag 1 and 40 from bag 2. So I'm going to stop right now and write down some stuff that they're giving me. Bag 1 has 25%. P sub 1 equals 0.25. And N sub 1 is equal to 40. P sub 2 is equal to 0.35. And N2 is equal to 40. No, I'm sorry. Oh, 50. I did that backwards. Dadgummit. This one's 40 and that one's 50. Erase. Blue. Let p hat sub 1 minus p hat sub 2 be the difference in the sample proportions of red crackers. Click. What is the shape of the sampling distribution of p hat 1 minus p hat 2? Well, we got to see what the shape of p hat 1 is, and we got to see what the shape of p hat 2 is. So here we go with p1. P1 is 50 times 0.25. And 50 times 0.75. Fourth is 10, 12, 10, 12. This must be 40, 38. You can round those, it's okay. As long as it's bigger than 10, they don't care if it's 12.2 or 12. So, approximately normal. And then I got to do 2, which is 40 times 0.35, 40 times 0.65. I don't know what those numbers are. 14 and 26. Greater than 10, approx norm. I'm sorry, that's way low for many of you guys. Let's do non-hieroglyphics. Notice what they did. They just did that number, this number, this number, this number, and just said all are greater than 10. I don't use the equal sign, but if you want to, you can. And because this one's approximate normal and this one's approximate normal, then, so I could say, so p hat 1 minus p hat 2 must be approx normal. Because that's what their question was. Describe the sampling distribution of p hat 1 minus p hat 2. And because p hat 1 is approximate normal and p hat 2 is approximate normal, the difference has to be approximately normal. Any questions about that? Find the mean of the sampling distribution. Well, the mean of p hat 1 minus p hat 2 is equal to p hat, about messed up, about put a hat there, minus 1. P1 minus P2, which is 0.25 minus 0.35 negative 0.1. You could have flipped that, I think. I don't think it told you which way to do this. But negative's okay. Beautiful. Click. Oh, that's how they did it. Good. And then I want the standard deviation. Standard deviation of p hat 1 minus p hat 2 is equal to this big old radical. And I'm going to put a 0.25. And I'm going to put a 0.75. And I'm going to put 140, 50. And a big old plus sign. And I'm going to put 0.35, 0.65. And I'm going to put 40. And I'm going to hit enter. And I'm going to punch the little finger in my exercises. Boom, 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 enter. But not before I say 40 is less than 10% of all, and 50 is less than 10% of all bag 2. This one's bag 1. You gotta say that. You gotta say it. And as good as you guys have done this year, I don't think there's any reason why you wouldn't. Click. Beautiful. Because 50 is less than 10% of all bags in bag 1 and 40 is less than 10% of all bag 2, you're going to plug all that stuff in and you're going to get 0.0971. And then they want to interpret that. So look at their interpretation. The difference between bag 1 and bag 2 in the sample proportions of red goldfish typically varies 0.097 from the true proportion of 0.1 negative. I would have liked them to say of a sample size of 50 for bag 1 and 40 for bag 2. But again, they got that typically varies in there. Just make sure you know how to interpret that. We've hit that a bunch, but there's a reason. That's asked quite a few times on the AP test. You may have to write it, and it may be multiple choice. Did you find it? Find it? I heard it. Everybody okay? Good, 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 good. Clicky, click, click. Estimate the probability that the proportion of red crackers in sample bag is greater than the proportion of bag in bag 2. I want it to be greater. P hat 1 minus P hat 2, I want it to be greater. Means it has to be bigger than 0. Because at 0, they're the same percentage. And when it's bigger than 0, then it's greater. And we've done all this stuff. We've already shown normality. We've shown the mean. We've shown the standard deviation. We've shown a direction. Those are the 3 things they want. Shape, center, spread, direction. And so I've already shown all that stuff. I don't have to do any more. But if it makes you feel better, and I love to do it, draw me a little picture and put what this is negative 0.1 and put over here, this was what? I forgot, 0.09, I think. Going off memory. And I want the 0 here, and I'm going to shade this in. But that just verifies the stuff that I've already written. You don't have to do it twice. As long as you can see what the mean and what the standard deviation and which way you're going, you're okay. Oh, the shape. I need the shape. And so then I'm going to go to my little calculator, and I got to find that bad boy. Let me go to an arrow. Exit. calculator. Normal, CDF. Number 2. Lower is 0. Upper is 9. This is negative 0.1. And was that negative point, or was it, I'm sorry, 0.09? 0.09, what, you remember what else? 7.1, thank you. That's kind of important. The more you can take that out, the more accurate you're going to be. And as this changes just a little bit, that changes my answer quite a bit. There you go, 1515. 1515 or 0.1515. You don't have to turn it to a percentage. Beautiful, beautiful, beautiful. Clicky, click, click. There it is. Look at that. They turned it to a z-score. You don't have to turn it to a z-score. We used to have to do that. You don't have to write normal CDF unless you just really want to. But if you write it, you better write down lower, upper, mean, standard deviation. You have to label each one of them. But if you already done it, there's no reason to write that down. We know you used your calculator. I used Desmos. Well, good. You better tell me what everything is still. Click, click. I hope, guys, you can calculate the mean and standard deviation of a sampling distribution and interpret the standard deviation. I hope you can determine the sampling distribution is approximately normal or not. I hope you can calculate the mean and standard deviation of the difference of two samples. And then I hope you can also determine if the sampling distribution is approximately normal of the difference. And then calculate normal probabilities. Yes, no, maybe, happy, happy, joy, doy. Did I let you down and say this was difficultly hard? Easy peasy, lemon squeezy, till you get to some of these questions. I'm kidding.